Welcome back. So we are going to discuss about the division and multiplication of complex numbers by use of the concept of transformation of a complex number into exponential and polar form. So multiplication. And division of complex numbers so we can apply the modulus argument form for dividing and multiplying numbers. So recall that given two complex numbers, Z1, let's say Z1 is given as R1 cos theta 1 plus I sin theta 2, and Z2 to be R2 cos theta 2 plus I sin theta 2. 1, the modulus of Z1 times Z2 is given by modulus of Z1 times modulus of Z2. And then number 2, argument of Z1 times Z2 is the same as argument of Z1 plus argument of Z2. And then 3, the modulus of Z1 divided by Z2 is the same as modulus of Z1 divided by modulus of Z2. And then number 4, argument of Z1 over Z2 is the same as argument of Z1 minus argument of Z2. So actually, these results are not very hard to check. For example, when you say Z1, Z2 is the same as, so modulus of Z1 and Z2 is the same as modulus of Z1 times modulus of Z2. You can recall that if you write Z1 in rectangular form, we have x1, y1, I, and Z2 is given by x2 plus y2, I. So Z1 times Z2 will be x1 plus y1, I times x2 plus y2, I. So this will give us x1, x2 plus x1, y2i plus x2, y1i minus y1, y2, because I times I squared is minus 1. So which will give me x1, x2 minus y1, y2 plus x1, y2 plus x2, y1, I. So if I'm to define the modulus of the product, will be simply the square root of x1, x2 minus y1, y2 squared plus x1, y2 plus x2, y1 squared. And then this is the same as just having x1 squared, x2 squared plus y1 squared, y2 squared minus 2x1, x2, y1, y2, the expansion of the first bracket, and then plus, here I'll have x1 squared, y1, y2 squared plus x2 squared, y1 squared plus 2x1, x2, y1, y2. So all these are under the square root sign. So this is the same as the square root you see this and this cancels out. So I just have x1 squared, x2 squared plus y1 squared, y2 squared plus x1 squared, y2 squared plus x2 squared, y2 squared, y1 squared, this last term here, this is 1. Then I can rearrange these terms and say this is square root. I bring this closer to this. So I have x1 squared, x2 squared plus x1 squared, y2 squared. Then bring this and this together. y1 squared, y2 squared plus x2 squared, y1 squared. So which is the same as square root of, common here is x1 squared into x2 squared plus y2 squared. These first two terms. And here common is y1 squared into y1 squared into x2 squared x2 squared plus y2 squared. Remember, summation can always commute. And then this is the same as the square root of x1 squared plus y1 squared. And then the inner brackets, this and this are the same. So x2 squared plus y2 squared. And from loss of indices, then this can be written as square root of x1 squared plus y1 squared times x2 squared plus y2 squared. And you see the first square root is simply the definition of modulus of z1, and this other one is the definition of modulus of z2. So therefore, modulus of z1 times z2 is the same as modulus of z1 times modulus of z2. So this is a quick proof of the first result. And you can actually, in a similar way, provide the result for this Roman 3. And then for Roman 2, argument of product. So argument of z1, z2. So you see, we are saying that Z1 can be written as R1 into cos theta 1 plus I sin theta 1. Z2 is the same as R2 cos theta 2 plus I sin theta 2. So if we multiply Z1 and Z2, then we'll have R1, R2 into cos theta 1 plus I sin theta 1 times cos theta 1, theta 2 plus I sin theta 2. So this will be the same as R1, R2 cos theta 1 cos theta 2 plus I cos theta 1 sin theta 2. And then this by this will be plus I cos theta 2 sin theta 1. I times I is negative 1. So minus sin theta 1 sin theta 2. So which will give us collecting real terms. So we'll have cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So this will be the real part. So this R1, R2. Plus I. So cos theta 1 sin theta 2. This other one will be plus sin theta 1 cos theta 2 for this term here. But we know that cos A plus B is the same as cos A cos B, and then minus sin A sin B, and sin A plus B is the same as sin A cos B plus cos A sin B. These are trigonometric double angle formulas. So the structure here, in this first, takes exactly the same structure as cos of A plus B. So this is simply cosine of theta 1 plus theta 2. So where A is theta 1, B is theta 2. And when you check the second part, this one here is actually taking the same structure as sine A plus B. So this will be sine of theta 1 plus theta 2. So Z1, Z2 will be given by R1, R2 into cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So which means that the argument in this product, Z1, Z2, is simply theta 1 plus theta 2, and argument of Z1 was theta 1, and argument of Z2 is theta 2. So when we add these two, we have theta 1 plus theta 2. So which is actually the same result as saying argument of Z1 plus argument of Z2. So that is what we have. So using this, we also remember that if we write Z1 as R1 e raised power theta 1 I, and Z2, we write it as R2 e raised power theta 2 I, then Z1 times Z2 will simply R1 R2 e raised power theta 1 plus theta 2 times I. That one can actually be seen from what we have here, that when you multiply, so this is what you have. So in exponential form, this part, all this bracket can be written as e raised power theta 1 plus theta 2 raised power I. So that's why I'm saying that Z1, Z2 is R1, R2 e power theta 1 plus theta 2 I. And then if you divide Z1 and Z2, it's the same as R1 over R2 e raised power theta 1 minus theta 2 times I. So these are very powerful tools that are going to help us to do some multiplication and division of complex numbers once you have written them in modulus argument form. So, example, express two cos pi over 5 plus I sine pi over 5 raised to power 5 in terms in the form a plus bi, where a and b are real numbers. So to work out this, recall that if z is given by r e raised power theta I, then z power 5 is the same as r. So we raise to power 5 both sides. So which is the same as z power 5 is the same as r power 5 e raised power loss of interest. This will give us 5 theta I. So in our case, r is 2 and theta is pi over 5. So it's like if we let now what is in the square bracket to be the z, so z to be 2 cos pi over 5 plus I sine pi over 5, then this means that z power 5 is what is going to be what we have as 2 power 5, because we're going to take r raised to power 5, and then e power, so r power 2 power 5 e raised to power 5 times pi over 2, pi over 5 I. So this is the same as 2 power 5 e power pi I. So this is 32 e power pi I which is 32 into cos pi plus I sine pi. And cosine of pi is -1, and sine of pi is 0. So we'll have 32 into -1 plus 0i. So this will give us -32 plus 0i as our solution for that equation. Then express two e raised power pi over 6i times √3 e raised power pi over 3i in the form a plus bi. So solution here. So R1 is 2, theta 1 is pi over 6, R2 is √3, theta 2 is pi over 3. So if you call this one as your Z1, call this number as your Z2. So Z1 times Z2 is R1, R2 e raised power theta 1 plus theta 2 times I. We'll have 2 times √3 e raised power pi over 6 plus pi over 3i. So this will give us 2√3 e power pi over 6 plus pi over 3 is going to give us pi over 2i. So which is the same as 2√3 into cos pi over 2 plus I sine pi over 2. So remember, the exponential and polar form are always interchangeable. So this will give us 2√3 cos pi over 2 is 0, then plus I. So this is the same as 0 plus 2√3i. Then example 2, express this quotient 2 into cos pi over 12 plus I sine pi over 12 over √2 into cos 5 pi over 6 plus I sine 5 pi over 6 in the form r e raised power theta I. So our numerator r is 2, theta is pi over 12. So we have r e raised power theta I, which is equals to 2 e raised power pi over 12i. And then denominator, r is √2, theta is 5 pi over 6. So we have r e raised power theta I is √2 e raised power 5 pi over 6i. Now, numerator over denominator will now give us 2 e raised power pi over 12i divided by root 2 e raised to power 5 pi over 6 I. And then this is just use lots of indices. So we'll have 2 over root 2 e raised to power pi over 12 minus 5 pi over 6 I. And 1 over 12 minus 5 over 6 is minus 3 over 4. So this will be 2 over root 2 e raised to power minus 3 over 4 pi I. But then you rationalize this side to get 2 root 2 over 2 e power minus 3 over 4 pi I, which is just root 2 e power minus 3 over 4 pi I. Then lastly, let z be 2 plus 2i then imaginary part of the product ZW be 0, and let the modulus of Z times W be 3 times modulus of Z. So use geometric reasoning to find 2 possible values of W, giving your answer in exponential form. So now, from this question, we have that modulus of Z times W is given by 3 times modulus of Z. So this tells us that modulus of W must be 3, since we know that if we define modulus of product of 2 complex numbers is the same as product of their modulus values. Now, imaginary part of the product is 0. That's what we're told. So argument of ZW must be 0 or pi. It because mean that the number is on the real axis. So now we can actually make this sketch. If this is the imaginary axis, this is the real axis. So Z will be somewhere here. So remember, Z is given as 2 plus 2i. So will be somewhere here. And this angle is actually, if you are to define a small right angle triangle here, then if I call this one theta 1, so theta 1 is tan inverse of 2 over 2 is tan inverse of 1, which is actually just 45 degrees or pi over 4. So this angle here is pi over 4. So since the argument of the product is 0 or pi, as the imaginary value of the product ZW is 0, then this other angle here, if this is pi over 4, then this must be 3 over 4 pi, because the total should be 180 degrees, or should be simply pi. So then argument. So since W can either be, the product can either be this side or this side. So this possible value of ZW, so this possible value of ZW, because the product ZW is actually, whose imaginary part is 0. So it means that it's on the real axis. So then if we call this one first and then this one second, then R, or the magnitude of ZW, which was already given from the question, 3 times magnitude of Z, and then we know the magnitude of Z. So if Z, so the magnitude of Z is given by 2 squared plus 2 squared. And so this is square root of 8. So the same as 2 root 2. So then now the W alone now has a modulus of 3. So the theta for W is either 3 pi over 4, or, so theta for W can be negative pi over 4, because the product of the two numbers must actually be on this real axis. So hence, possible values of W's are, W is either 3 e raised power minus pi over 4, or W can be 3 e raised power 3 pi over 4. Then you have an I here. So that is how we can use geometric reasoning to get the possible values of W, because first step, we have been given the product ZW, its modulus, given as 3 times modulus of Z, and from the property that the modulus of product of two complex numbers is the same as product of the modulus, then you simply use this formula and equate in what you have been given. You should get that the modulus of W is 3. So then now, modulus of W is 3, doesn't change. So in the expression of the complex number W, which will be of the form e raised power theta I, R will be 3. So the next part will be now to interpret how to get theta. Further, we were told that the imaginary part of the product ZW is 0. So when imaginary part of the product is 0, then it means that the product lies on the real axis. Because on the real axis, every value of the imaginary part in the complex number is 0. So the ZW lies on this axis. And then we have now to use geometric reasoning now to find the two possible values of W. So W has modulus of 3. And since the argument, since the imaginary part of ZW is 0, then it can either be on this positive side of the real axis, whose value will be 0, or now you make a full rotation on the real axis in the anti-clockwise direction to get the angle as pi, still on the still on the real axis. Now, because already we know that the complex number Z is in this first quadrant, then W has modulus of 3, then it means that the angle that W makes with the angle that W makes with the axis can either be this 3 pi. So remember that also what we are using here is that argument of is the same as argument of Z1 plus argument of Z2. That since we are saying that argument of the product is either pi or 0, so we know that the argument of Z1 or argument of Z is actually pi over 4. So this one is not changing. So this actually is what you are calling ZW. So argument of ZW is the same as argument of Z plus argument of W. So this one, if it is pi, so we'll have pi, and then this will give us, this doesn't change, it's pi over 4. Then say this is the unknown, argument of W. So then now you can easily find argument of W will be pi minus pi over 4. So which is giving us 3 pi over 4. So that's one possibility for the argument of W. Or when now the argument of the product will equate to 0, then we'll have 0 equals to pi over 4 equals to argument of W. So which means argument of W is going to give us 0 minus pi over 4. So this will be minus pi over 4. So therefore, there are two possible values of argument of W, either 3 pi over 4 or minus pi over 4. And now once you have the values of argument and you know the value of R, then you see that these are the two possibilities for the complex number W, either 3 e raised power minus pi over 4i or 3 e raised power 3 pi over 4i. So that's what we do in that case. So in the next discussion, we'll be discussing about the De Moivre's theorem, which will be useful in finding the powers of complex numbers and roots of complex numbers. Thank you.